Hi everybody, this video is about tuning your controller or finding your P, I and D values for your feedback controller. And we're going to discuss the methods of Ziegler and Nichols. Ziegler-Nichols is all about tuning your PID controller by using measurement data, so input and output data in the time domain. And it's used quite often in process industry and not that much anymore in motion control, because often in motion control you define your controller parameters by using techniques in frequency domain like loop shaping. For Ziegler-Nichols, we are going to use the parallel PID implementation. And in a parallel PID implementation, the transfer function of my controller, output divided by input, and the input is the error of the signal, is equal to a proportional gain, Kr, with an accent over here, times 1, so this is proportional action, plus 1 over S times tau I, which is the integrating action, plus S times tau D, which is, together with the Kr, your differentiating action. There are two methods which we will discuss, which are the oscillation methods of Ziegler-Nichols and the steps response methods. Let's start with the first one, the oscillation method. I have here a feedback system, and this is my controller, HR, which could be a PID type, a PI, etc. This is my process, and this is the subtraction of my set point and my output value over here. What we are going to do is the following. We are going to replace this controller by just a proportional one, just one P action, so just a gain KR. We're going to increase that gain Kr just to the point that oscillation occurs. And the value at which oscillation occurs, we call that Ku. So that's the oscillation value of Kr. So the value at which oscillation starts is Ku. And we're going to measure the period of the oscillation, which we call Tu. And based on that, we can derive a set of parameters for setting the Kr proportional gain, the Ti, the tau I, which is the integration constant, and the tau D, which is the derivative constant, so of the differentiator. Well, how do we do it? Suppose we want to use a P controller. Then we set the value of Kr to 50% of Ku, the value of which the system started to oscillate. When you want to implement a PI controller, you have to set Kr to 0.45 times Ku, and that is somewhat lower than with only a P action because the integrator will not help in stability. So we have to increase the gain margin at something more. And tau I can be set to 0.8, 80% of the oscillation time Tu. When you're going to apply a PID controller, you can increase the Kr to 60% of Ku, so the value at which the system starts to oscillate. Define the integration time constant tau I to 50% of Tu, and define the differentiating time constant tau D to Tu over 8, so 0.125 times Tu. That's the oscillation method, but not every system may brought into oscillation or will even start oscillating. So there is another method Ziegler-Nichols defined, which is the step response method. And in the step response method, we apply a set point, a step set point to the system, and we look to the output of the system. And we measure that output, and when it has this kind of a behavior, a delay and a kind of first order system approach, we can define the delay time, we can define the time constant of the system, and we can define the process gain. And why is that? Because when we have a system response which looks like a first order behavior plus a delay, then this is my transfer function. HP is the first order system description, in this situation done in frequency domain, so it's Kp divided by 1 plus j omega times tau, and that has to be multiplied with the system description of a delay, which is equal to e to the power minus j times omega times tv, in which tv is the delay constant. So how can we derive tv tau and kp. Well, tv is the delay time over here. So it's the difference between the time the output starts to change minus the time that the step has been set to the input of the system. Tau can be derived by looking to the 60% value of the 60% of the end value of my system, and then look to the time um, at which this value occurs, and the difference between that time and the starting time of my output curve is my time constant tau. And Kp is the static gain of my system. Well, in the static situation, everything is stable and constant, so all the derivatives of a um, static number, so a constant number, are zero. So also omega is zero. So in that way, my system, HP, is in a stable situation, Kp times 1 and divided by 1, so it's Kp. So Kp can be calculated by looking to the static situation, looking to the end value of the output signal and dividing it by the value of your step input signal, and then you get Kp. So now we have established TV, the delay time, the tau, the time constant, and the static gain Kp. But there's also another possibility in how the output signal could be visualized, and suppose that the output signal has this kind of a response. And then we could say, well, this looks like a delay, and well, over there's something which we can call the time constant. What is the approach? Well, we look to the steepest point of the tangent, we draw a line, and we have two intersection points here at the end value and here at the zero crossing value. And the time between the intersection point over here and the intersection point over here, we call that time constant tau, so the dominant time constant of my first order system, and the time between this intersection point and the point that the input signal has been applied to the system is called the delay time TV, and Kp can be calculated again using the same method as discussed with this output shape. Well, when we have that, we can use another table of Ziegler-Nichols, which is this table. First of all, let's look to a P controller type. When we want to use a P controller type, we can define the multiplication of the proportional gain times the gain of my system, so Kr times Kp, as tau over Tv. So when you calculate tau and you divide tau by Tv, you get the product of Kr and Kp. So Kr is tau divided by Tv, and that divided by Kp. When you have a PI controller, if you want to use a PI controller, you can set the Kr value to 90% of this value and then divide it by Kp. The tau e, the tau I should say, which is the integral constant of the PI controller, can be set to 3.3 times the delay time. And when you use a PID controller, well, we can use this factor times 1.2 divided by Kp. So then we have the Kr. Tau I can be calculated by multiplying the delay time by 2, and tau d can be calculated by multiplying the delay time by 50%, so by 0.5. So then we have the parameters for my controller, the P, the I, and the D. Let's let's use an example to calculate the values for a certain controller, use up some so-called measurement or calculation data. And in this example, I have this curve of my output signal. So I applied an input, a step input to my system with a step which is equal to 2, and this is the outcome of my system. So this is the response function y, and we can see that the end value of y equals the value of 6. Okay, so now we can see that this is more or less a first order approach with a delay. So we can apply this formula, this transfer function for the process, defining it as a first order system, Kp over 1 plus j omega times tau, multiplied with the transfer function of delay, e to the power minus j omega times Tv. Now we can calculate the tau, the TV, and the Kp. What we are doing is we are drawing a line at the tangent at the steepest point of this output curve, y, and at these intersection points over here, the maximum value, and at the zero crossing value, this time we call that the time constant tau. So in this case, tau is equal to 3 minus 1 is 2. Well, that's written over here. TV is the time between this point and the starting time of the output curve, so this intersection point by minus the time over here, which is 1 minus 0, which is 1 second. And Kp, we've seen that is the static value of the output signal divided by the step value, the input signal, which is in this case 6 over 2, and that is equal to 3. So now we have Kp, TV, and we have tau. And suppose we want to use a P controller. Well, we have to use the table again, look up what the values are for Kr times Kp for a P controller, and we can calculate Kr. So Kr times Kp is tau over TV, so it's 2 over 1 is 2. And we can calculate Kr, which is equal to that value of 2, which has been calculated over here, divided by Kp, so it's 2 over Kp, 2 over 3, which is 0.67. Well, that's all about Ziegler-Nichols, and Ziegler-Nichols gives you by these approaches a very good starting value for your Kp or your Kr, your integration constant, and your differentiating constant. These are starting values, and make sure that you look to the specifications of your system to see whether these values have to be changed somewhat or not. All right, thank you for watching, and I see you in the next video.